Good morning, everyone. Welcome to our locomotion webinar, which is called Net Zero Emissions, Zero Pollutions, Inconvenient Pollution Truth about the Green Energy Supply Chain, organized by the EB, the University of Valladolid, and BC3. My name is Kati Wiese, and I'm working for Economic Transition Policies for the European Environment Bureau, which is the largest, one of the largest umbrella organizations for environmental organizations from all over Europe. So we came together today as there's no doubt that we need a large-scale deployment of renewable energies to meet the Paris Agreement, but nonetheless, we also have to acknowledge that no energy source comes free of environmental and social side effects. And that's why we have invited experts today to present what these costs are and how can we avoid them. In terms of agenda, after first introduction to locomotion from my side, we will hear a keynote on the hidden material costs of the green technologies, and we will also see the alternative policy options that you as participants can vote on. Afterwards, we will see the results of that exercise, and then we will hear from some of the hidden societal and environmental costs by our invited speakers, which will be followed by a Q&A. And just briefly for the Zoom etiquette, we will invite you to use the chat for comments, or if you would like to exchange with each other. And please use the Q&A box for questions. So I would like to start with briefly introducing locomotion. Locomotion stands for a low-carbon society and enhanced modeling tool for the transition to sustainability. And it's a Horizon 2020 project that aims to develop scientific models to assess the socioeconomic and environmental impact of different policy options. And in that way, to help different stakeholders and society, like scientists, politicians, policymakers, civil society, to make informed decisions about the transition to a more sustainable future. It's a very interdisciplinary project with 14 different partners from all over Europe and from different sectors such as academia, think tanks, and civil societies. And you can see all the partners here on the right. So locomotion thus aims to design a new set of integrated assessment models. And if you wonder what that means, integrated assessment models, or in short IMAs, are tools and models that are designed to help us to understand how human development and societal choices affect each other in the natural world. And they're called integrated because they combine different strands of knowledge. And the model of locomotion is called William. And William builds on existing IMAs developed by the previous project, which is called Medeas. And it also includes knowledge from other relevant models, such as World 6, and has also a number of other improvements. For example, it will have a greater geographical coverage and increasing detail and provision of the models, and it will also be able to integrate demand management policies, and the idea is also to make it more user-friendly. And you also see here some of the components of our model. So we are currently halfway in the project because it started in June 2019. So all our research partners are currently very busy with integrating the different components into one model. And we're expecting the first results in autumn. So we also invite you to follow our social media channels, which we'll post in the chat, to keep yourself updated. That also means that the results from the presentation today are based on Medeas and other previous models. And at that stage here, we would also like to highlight, of course, that complex IMAs are not free of imperfections and limits, as they must try to capture societal preferences and habits and behaviors both now and in the future, which is challenging, of course. However, despite their limitations, they remain a very valuable tool to explore different choices that will contribute to a low-carbon society. And with that, I would like to introduce our first speaker, Inigo Capellan-Perez. He's a postdoctoral researcher for the University of Valladolid. Please, Inigo.
Good morning, everybody. Thank you, Kathy, for the introduction. Okay, so I'm going to focus on the material requirements of green technology. So in general, the important or the key message here is that sustainability is a multidimensional concept, and we all know that we need to go for 100 renewables or very high share of renewables, but we have to keep in mind that there are other dimensions which we need to tackle in order to achieve a true sustainability transition. So please, next slide, Kathy. Okay, so with relation to material, and after my colleagues will talk about this other kind of impacts, the important thing here is that maybe it sounds like a paradox that even if renewable power plants use renewable flows of energies, they are made of non-renewable materials. So just with this first assumption or this first information, we can reach that a renewable-based system will have higher material requirements and diversity than a fossil fuel-based system. This is due mainly to three things. The first thing is that the power density, which means how much energy we can extract per area of per surface, per square meter, as it is shown in the figure in the slide, it is much higher for fossil fuels, simply because they are concentrated deposits of energy, which are usually below the ground, and which the forces of geology and time have concentrated into high deposits. So here we can see that in the figure we can see in green the different renewable technologies which have around 1 order of magnitude less or 2 order of magnitude less than fossil fuels. This is due to the fact that renewable energy by nature, by its biophysical characteristics, is dispersed energy. Okay, so here I have put as an example in the figure the global average solar irradiance. So of course, any facility which is going to use this solar irradiance due to thermodynamical losses will have lower power density. Okay, so next, yes. And there is also one thing important, that most renewables are useful for providing electricity, typically wind and solar, but electricity is just a minor part of our energy consumption, typically around 20 or 25%. So even if there are uses that can be electrified, let's say, easily, there are different uses that are extremely difficult to electrify because they need high density fuels. Typical examples are freight transport, high heat temperature in industry, aviation, etc. So for this kind of uses, electricity is not useful. So if we want to do or to do synthetic fuels such as hydrogen, the second law of thermodynamics is going to tell us that in order to concentrate a lot the energy is going to require a lot of losses. And a lot of losses means that we are going to need to build a higher capacity. And this higher capacity means more materials, more land requirements, more investments, etc. Next slide. And a third, sorry, no, it was this third figure, thank you. And then there is a third element which indicates us that the renewables-based system will have more materials, which is the fact that because renewables are variable, we will need to build a system in order to manage this variability. So this will mean more devices, more maybe overcapacities, etc., more storage, etc. So these additional devices will require additional materials. So now next slide. So once this is clear, many questions arise, no? For example, which amount and of which materials will the transition to sustainable energy systems will require? How much of these materials will come for recycling or from mines? Also, it's very important how many materials will be demanded by the rest of the economy. So here we can give an easy example, maybe with lithium. No, so the energy transition will require lithium, for example, for electric cars, for electric storage, but we are going also to need lithium for our electronic devices, for computers, for mobile phones. So this is an important question also. Another interesting question could be to identify which are the potential critical materials in this transition. So in this sense, for example, the European Union already 11 years ago in a pioneer work launched this critical raw materials task within the Commission. And other questions, okay, we can have a critical material, but what are the potential for substitutions of these critical materials in energy technologies? And which are the trade-offs? Typically, is lower efficiency. Also, we can move to more geopolitical dimensions. For example, where are the mines of these minerals? Also, where are they being recycled, etc. So in general, the topics of minerals and the energy transition, let's say that it is quite new, apart from the European Union, which already for 10 years, more than 10 years is working on it. Other international organizations such as the International Energy Agency or the OECD have launched only very recently reports, as you can see in the slide. Okay, so next slide. Okay, so now I would like to show you some of the results of our simulations, which are all based on these 3 publications, in which we have explored some of these questions, mainly the question of how many materials do we need for the energy transition, and we have built some indicators of criticality or scarcity. So next slide. So first I will start with some data, and then I will show some results of the simulations. So in this table, you can find the amount of kilograms for a typical wind farm of 50 megawatts. No? So 50 megawatts, if each windmill has 2 megabytes, we can think about 25 windmills. Just to give you the magnitude order of the amount of materials. So here, for example, we will need in the order of 7,000 tons of steel and iron, 1,000 tons of copper, another 1,000 tons of aluminum, and then we are going to require other minerals in lower amounts, such as nickel, neodymium, and dysprosium, mainly for permanent magnets. So here it's important that even if these amounts of neodymium and dysprosium seems low, at the end everything is relative, and they are low or high with relation to their availability. So we will see that with the simulations. So for solar, next slide, I show something similar, a table with the typical mineral requirements of, okay, this is average with the current sub-technology mix. So maybe the first remark is that the table is much longer, no? It has many more elements. But also, if you look carefully, you will notice that the intensity of these materials, the amount of material for the power plant is higher in relative terms than for wind. So iron is almost 10,000 tons, aluminum again, copper, steel, chromium, manganese, etc. Then at the end of the table, we again have some minerals which are required in a relative low amount, such as tellurium, indium, vanadium, or gallium, but we will see they are very interesting because they allow higher efficiencies of the PV. And in the slide, in the picture, you can see what does a 60 megawatt photovoltaic solar plant looks like in real world. No, so it's big, and I would like to link here with the presentation which Dirk will do later on about the solar land footprint. So this is already telling us that the impact in land is not going to be negligible when we scale the transition to high levels of penetration of renewables. Okay, next slide. Okay, another technology that we have researched in detail is the technology of electric batteries, especially for vehicles, for transportation. So here we have done more in-depth work, and we have analyzed we have gone to the level of sub-technology. So this means that not all electric batteries are the same, but different companies are developing different technologies based, if you notice in the table, based on different metals. For example, the LMO in the first column uses aluminum, copper, lithium, manganese, graphite, and an amount of plastics. And then we have some others, which, for example, use cobalt and nickel, NMC, and also NCA, which is the one used by Tesla, for example. And then we have a technology, LFP, which uses lithium, iron, and phosphorus. And this one, for example, if you know, see, doesn't use nickel and cobalt. So I don't have here too much time to enter into details, but of course, different mineral compositions mean different performances. Okay, technical performances, efficiencies, lifetime, weight of the battery, etc. So here we have taken, let's say, real models, and we have also included some estimations for the material requirements of the chargers, because the electric car needs to be connected. I mean, in order to be charged, need to be connected to the grid. So here we also have additional material requirements, which we account for. Next slide. Okay, so once we work in detail the part of the green technologies, let's say, we have to take into account what I mentioned at the beginning, not that the rest of the economy is also going to demand materials. So here, the first maybe point to say is that data are a problem, because globally there are no robust databases, and also, I mean, one of the main things that complicates this issue is that the supply chain of minerals is very complicated. So minerals can be extracted in one country, refined in another, then exported in another one. So all this makes that we have a problem of data. So here, there are some studies which, with this problem or this barrier, they don't enter into this issue. But what we decided to do here is to do some regressions of the demand or the consumption of materials, the historic consumption of each material, and do a regression as a function of the GDP. So this was explorative work, but we found that the regressions fit quite well. So this is what we are extrapolating into the future in the model for the rest of the economy. Of course, we avoided the double accounting by subtracting in the historic period the part of the bottom-up green energy technologies to avoid double counting. Next slide. Okay, so let's say that with this raw data, we introduce them in an integrated assessment model, as Kathy was explaining at the beginning, and then we build a scenario which we could call him a green growth with 100% renewables in 2060. Why green growth? Because it has the following characteristics. It has a lot of economic growth. There is less population growth than in the past. The penetration of renewables increased very fast. We reached 100%. We set the scenario to reach 100% in the mid-century. Efficiency improvements faster than in the historic period, and also a transition to electric vehicles. So here, maybe the only feature which does not correspond exactly is that we consider the current recycling rates of minerals as constant. This is just, let's say, as an impact analysis to show you now the results without this factor. And then after my presentation, you will have the opportunity to decide about some simulations changing this recycling content. Okay, and then the main outputs, which I'm going to show you, is basically a ratio between the required minerals to be extracted from the mines versus the availability, and we use for that reserves, the current estimated reserves. So here something important about the model is that we we consider material requirements with relation to availability just as warnings. So there is no feedback on demand in the case that, imagine we surpass all the current reserves and we consume, I don't know, 150% of the reserves of one mineral. But we decided not to feedback in the model this effect, first due to complexities for this feedback, and also because there is a lot of uncertainties about the level of current reserves. Okay, so next slide. Also, you will have the opportunity to modify this assumption in the simulations, with live simulations with David later on. Okay, so what are reserves, which is the indicator we are going to use? Basically, in geology, there are two types of indicators which are the most used, which are reserves and resources. So reserves refer to amount of materials which are assessed to be extractable from a technical point of view and an economical point of view with current technology and at current market prices. While resources is an indicator with much more uncertainty, where it is thought that there is an amount of material down there, but it is not exactly known how much there is, what quality, how difficult it is to extract, etc. So you can imagine that no one knows exactly how many of these materials there are in the crust of the earth. So these estimates are inherently subject to uncertainty. Okay, so and we use data from the US Geological Service, which let's say are quite standard for the comparison. So next slide. Okay, so now this is already some results. This first slide is showing of the total demand of materials, how much comes from the energy system in our simulations by 2060. So this is telling us from the point of view of the total economy, if a material, due to the transition, if a material is going to increase a lot or not, the extraction that will happen anyway without any transition. So here in red, we can find the materials that we find that are boosted with the energy transition, which are tellurium, indium, lithium, tin, and silver. Then we have another category where the extraction is estimated to increase between 10 and 50% due to the energy transition. And then we have a small group of chromium, magnesium, vanadium, and zinc, where the energy transition in principle is not expected to increase a lot their demand. Okay, next slide. So this is with relation to the comparison of the energy transition and the total demand. But if we can do the comparison with relation to the accumulated extraction with relation to reserves. Okay, so this is what this figure now is showing. And we can see that for several cases, we see that the extraction will be much higher than the level of reserves. In the case of tellurium and indium, it's really high, 29 times, 17 times, but we have other cases, tin, 6 times, silver, 4 times, gallium, 2 times, and then we also have lead 1 time, copper almost 1 time, lithium almost 1 time. This is only mineral requirements for the energy transition. And next slide will show you the total extraction. So green technologies and rest of the economy with relation to reserves. Of course, the size of all the bars increase. It increases more for others, for some than for others, but we can see that in general, we bring most materials over the level of reserves, with the exceptions of vanadium, magnesium, aluminum, and zinc. So next slide. Okay, maybe I will skip this. And then, okay, I'm going to enter into the part of the, starting to introduce the next part of the seminar, because we are going to give you the option to repeat this same scenario, which I have shown you the results, changing a couple of hypotheses or a couple of inputs. One of them is going to be the recycling rates of materials. So here in that table, I have collected the estimated current global recycling rates of the materials we model. So I have no time to go, of course, one by one, but you can see that for most of them is below 50%. And for many of them, which are very critical, we are even in 0%, dysprosium, neodymium, tellurium, vanadium. So here I will just say that recycling is not only an issue of having a wheel at the end of the life of the product, but it has to be done ex ante. So the products need to be designed to be recycled. And also, of course, the recycling needs to be profitable. So next slide. Okay, and the second, I already mentioned a bit, that there is the question of mineral availability, no? That there is an uncertainty about how much we could extract with the current technical knowledge and the current market prices and so on. But also I would like to highlight that this availability depends, of course, on these market factors, in which we have to include also speculation. We have to include geological factors in the sense that there are many interdependencies. So minerals are not extracted as fossil fuels. So when you have a oil field, you extract oil, maybe a bit of gas, but no more. When you want coal, you extract coal. But for minerals, many times, many metals are extracted as co-products of others. Okay, so it is not easy or so simple to estimate their availability. And then, of course, due to the high pollution of mining and water consumption and so on, there may be regulation issues which, due to protection of environment and or societies, will reduce this availability. So next slide. Okay, so with this in mind, we would like to give you the option to choose between 4 scenarios to repeat. So on top of the baseline scenario of green growth with 100% renewable in 2060, which I've shown the results in the slides before, we would like to give you the opportunity to choose between these four scenarios, and we can see together the results and discuss them later. So the scenario A will be to improve by 50% the recycling rates and assume that reserves are in reality double than what it is now estimated. B will be the same, but instead of 50%, 100% increase. C will be an option where we consider half current estimated reserves and 50% recycling rates. And D, it will be the same, half estimated reserves, but doubling the recycling rates. So now, yes, great. So you should have a poll should have appeared in your screen where you can choose between one of these 4 options. So we will give you some seconds to think a bit and select. And then the most voted option will be simulated by David, which will continue with the presentation from now on. So thank you very much.
Thanks a lot, Inigo, for your presentation. Yeah, so we will have maybe 1-2 minutes for you to decide, and then David Alvarez Antelo, who's a doctoral researcher from University of Valladolid, will present the results.
Well, I see there are a couple of questions in the Q&A. Are we waiting till the end for that? Or?
Yes, so we have a Q&A after our presentations at the end. Okay, I think, Martina, we can show the results now. Okay, so it was quite close, but most most of the people would like to see the last scenario, improve 100% recycling rates by 2050 and half of the current estimate reserve. Yeah, with that, I will hand over to David.
Okay. Good morning, everybody. I'm going to show the software to simulate the most voted scenario. Can you see my screen?
Yes.
Okay, thanks. At this time, the idea is to simulate the chosen scenario, in this case, the DS scenario, and see some results regarding the total demand of materials. First, to better understand the different dimension, because the D option have two dimensions, the recycling rates and the increasing the amount of reserve. We are going to do any dimension separately. One simulation with the baseline with improving the recycling rate, other simulation only with the increasing the amount of reserves, and the final simulation with all the options at once together. So we're going to start with the first option, the baseline scenario, with the improve in the recycling rates. I'm going to put the name of the simulation. And now I'm going to improve directly in the variable the recycling rates, multiply by 2, and simulate until the end of in the final time. In this case, the 2060 year. Now I will to show you the results in terms of bar graphs. What you can see in this graph is the relation between the total demand of materials, the total cumulative demand of materials, respect to the expected reserves. You can see in the x-axis all the materials in this model, and in the vertical axis is the relation or ratio between the total demand of the different materials respect to the expected reserves. Sorry, in the final time, the 2060 year. In this graph, we have the two simulations, the baseline scenario with this color and the baseline with the improving the recycling rate. You can see, for example, for the indium, in the case of the baseline scenario, this bar, the total the amount of demanded of the indium of the whole economy is higher than 50 times the estimated reserves. And if we go to the tellurium, we can see that the total amount demanded is close to 30 times the estimated reserves. And the performance simulation with the improving the recycling rate, you can see that all the materials reduce the total needed demanded material for all the simulation. And you can see the difference between materials because, for example, indium start with a recycling rate higher than tellurium. Tellurium are a starting recycling rate and current recycling rate very low, close to 0. So improving the recycling rate doesn't reduce appreciably the needed demand of material. You can see that all materials except aluminum, magnesium or vanadium surpass the total estimated reserves. The one line here. Okay, and now we are going to simulate another dimension, the half of the estimated reserves. In this case, we are going to reduce the estimated reserve by half, simulate. And show the same bar graph. Okay, the new simulate are this color, these bars. You can see that respect to the baseline scenario, there is an increase in the total amount of material needed to obtain the green growth scenario of 100% renewable electric energy in the final year. In all material, there is a improvement, obviously. And if we perform the final simulation with all the options, with the HAL reserves, the cut in the reserves, and the improve in the recycling rates, so we reduce the estimated reserves and improve the recycling rates. So there is all the different simulation. The baseline scenario is this bar, the improving the recycling rate. If we cut the reserve to half reserves, and the two options together. This is the bar graph that represents if we improve the recycling rate of all the materials, but estimate that the reserves are half than the current reserves estimated. You can see in all materials is that even if we improve the recycling rate, all demand of materials surpass greatly the estimated reserves. Only for aluminum, magnesium, or vanadium, we are able to obtain the green growth scenario of 100% renewable electric energy without surpass the estimated reserve. All the other materials need several times the estimated reserve to obtain the green growth scenario. In other words, if we need to reach the green growth scenario with 100% renewable electric energy, we need to multiply by 60 times, in this case, the total amount of estimated reserves, or 30 times in the baseline scenario. For what kind of use as my colleagues show, there is some materials like cadmium, gallium, indium, silver, and tellurium that are needed in higher quantities to solar photovoltaic technologies. Other materials like lithium goes to electric vehicle batteries or mobile batteries or lithium batteries. Silver is another material that are in many technologies, in solar technology, electronic technologies, and copper are in all renewable electric technologies, in solar technologies, photovoltaic, in wind, or in lithium batteries, there is a considerable amount of copper. So even in this scenario of improved recycling rate, as I say previously, the need of these materials that will need to accumulate to obtain this scenario are much higher than all the estimated reserve in the world Earth. And that's all for my part, for my side. Thanks.
Thanks a lot, David. And yeah, it was great to have a kind of live simulation here right now. And thanks a lot for your explanations. So maybe you could close your screen sharing, and then
Yes,
I will share my presentation again.
Okay.
Okay, thanks again, you both. Now we hear a bit more about the hidden costs and limitations of the EU energy transition. And our first speaker will be Madja Midavida. She's a professor for the University of Valladolid, and she will talk about the hidden cost of electric cars. Welcome, Marga.
Hello, Kathy. Hello, everyone. And well, I would like to talk a little bit about the minerals needed for the electric cars or for electric mobility, which is based on the same models that Inigo and David have explained. And please, next slide, Kathy. And it's based on these two papers that were published last year that talk about the limits of transport decarbonization. Next. Well, in these papers, we ask a question. The question is if how could we decarbonize transportation at world level? So we know that the Paris objectives that require a stronger decarbonization of transportation tell us that we should have an almost carbon-free transportation by 250. So we ask our model how to do this. So here we see that the emissions of transportation, this is the data at world level, have been rising since 1995. And in order to meet this objective, we should have almost zero emissions by 250. Here we didn't contemplate the complete decarbonization, the 100% decarbonization of global transportation. We were a little more modest, and the objective was only 80% decarbonization. So, okay, let's say this is the objective that we have in mind. And in order to find it or to meet it, we set three scenarios. The one which is in yellow is the past trends, just continuing with past trends of recycling and of energy consumption and of electric vehicle change and do nothing. The second is the electric vehicle high scenario, where we have a very strong transition to electric vehicles. And the third one is a scenario where we don't rely only on electric cars, but we rely on very light vehicles. We switch to motorbikes, we switch to bikes for the mobility in cities, and so on. Next slide, please. So this is the amount of vehicles, or the share of vehicles that we will have in these scenarios. This slide is for household vehicles, for small vehicles for people, no? For moving persons. So we have in the first line the share today. You can see that most of the cars are gasoline or gasoil cars. And at world level, there is also a very strong amount of motorbikes. Many of them are electrical. You can see that the electrical motorbikes are in yellow. This is because of China. China policy of motorbikes has enhanced electrical motorbikes a lot. And the rest in gray are gasoline motorbikes. And if we continue with the present trends and do nothing, by 250, there will be an important share of electric cars, which is the one in blue. And this share will be almost the same as the one of gasoline cars, which is in green. And we will also have a lot of electrical motorbikes if the trend of electrification of motorbike continues as usual and extends to other countries and not only to China. And the rest will be gasoline motorbikes in gray. Well, this is the present trends. No? So we have a lot of mobility, electrical mobility, but this is not 100%. So in the scenario EV high, we have complete electrification of cars, which is in blue, and of motorbikes. But you can see that we don't change the share between motorbikes and electric cars because in this scenario, we're not changing the cultural habits. And in the next scenario, in the e-bike scenario, we do change these cultural habits. And you can see that most of the vehicles are motorbikes. This means that the people will switch to light vehicles, which could be motorbikes or very light vehicles, similar to motorbikes, but they may have 4 wheels. There is a high increase of electrical bikes for mobility. And cars are a small minority. And in this scenario, we didn't electrify all the cars because this scenario is more modest on electrification. And so we can see the changes in the mineral requirements of this scenario. Next, please. But for the transportation of goods, the problems are much more difficult to solve because it's a lot more difficult to electrify a truck than to electrify a motorbike or a car. And this is because the trade-off between the weight of the battery and the weight of the load is an important technological limit. So today we have that the share of vehicles is this one that is in the first line. Most of the trucks are gasoline. Most of the vans are also gasoline. Most of the buses are gasoline, and half of the trains are electrical, and the rest are moved with gasoil. If we continue with present trends, most of the trends of the trucks will still be based on gasoline because gasoil, sorry, because there is almost no electrification today of trucks. The vans could be electrical in an important share as the light vehicles. Buses are getting electrified, so we could expect that we could have also an important share of electrical buses, and trains will remain as they are now. If we go to a scenario of very, very high electrification, what we assume is that the trucks could be hybrid in an important share. Almost all the vans could be electric, almost all the buses, and all the trains. But for the trucks, it is quite difficult to have all the trucks being electric. So we have this modest scenario of not electric, but hybrid trains. And in the e-bike scenario, we have 100% electric train. Buses are only half electric. Vans are almost all, but not all of them. And trucks are still moving with gasoil, sorry. Next, please. And we can see the results of these scenarios in terms of greenhouse gases emissions. You can see that the trends scenario will only enable us a 20% reduction of, less than 10% reduction of emission compared to the, excuse me. In the trend scenario, we are not only not reducing the emissions, but we are increasing them. The electric vehicle scenario decreases a little bit, but and the electric bike decreases almost at 20%. But you can see that these scenarios are very far from the 80% objective of the decarbonization. Why? Because there's a lot of mobility that is not so easy to electrify. And so the objectives are not met. Next. And for the minerals, we can also see here the results. We have the results for different types of batteries, as Inigo has shown, that the batteries may evolve in different technologies. So these different colors stand for the different types of batteries. And we have here the three scenarios: trends, electric vehicle high, and electric bike. And in the trends, we have present recycling rates, but in the other two scenarios, the recycling rate have been doubled. And for lithium, we have that in almost in all technologies, the electric vehicle scenario, well, in all technologies, the electric vehicle scenario has depletes the reserves. See, and it depletes the reserve in all the technology and in a important percent. Even the e-bike scenario, which is a very disruptive scenario from the point of view of the social habits, depletes the 100% of the lithium in some technologies, and in some others is close. Next, please. For the cobalt, we also have the same. The electric vehicle, the high electric vehicle depletes the reserves of cobalt for most technologies, and even the electric vehicle scenario is close. Next. Next, please. And for nickel, we also have the same problem. Although for nickel, the main use is the rest of the economy. It's not the electrical batteries, the electrical batteries, the batteries for the electrical cars, sorry, is an important consumption, but the rest of the economy is the biggest. Next, please. And finally, we have the results for copper, which is also important. And the contribution of the motors and the charging infrastructures is important, although the biggest contribution is one of the rest of the economy. Okay, well, this is all from my side, and well, we can discuss this in the debate if there's time and there is any questions. Thank you very much.
Thanks a lot, Marga. Thanks a lot for your presentation. So then we would like to move to Dirk-Jan van der Ven, who is a researcher, a postdoctoral researcher for BC3 BAS Center for Climate Change on the hidden land costs of solar energy. Jan, Dirk, do you want me to stop sharing?
Yes, yes, please. So do you see my screen?
Yes, works well.
Okay. Yes. Hello, everybody. I'm presenting some work that we did recently about on the land occupation of solar power energy and the effects of that. So to the background. So solar energy is going increasingly important for the energy transitions in most policy planning. It's because the solar resources are abundant, like it is sun everywhere. So the idea is that you can generate it everywhere. It has zero emissions, in direct sense. It's less visible and noisy than wind energy, which is a lot of times why wind energy is increasingly complained about. And also it's cheaper, and it's getting very quickly cheaper. So in the last decade, it has become from a quite expensive energy technology to the cheapest energy technologies for new capacity in many places. and costs are still declining. So it's of course that makes it a very interesting option for the energy transition. However, land occupation of solar energy is important. It's not negligible at all. So it needs a large amount of horizontal space to capture sunlight, and this is, for example, already are different with, for example, wind energy, where you can easily combine wind energy with other land sources. But solar energy, you need all the land horizontally, so you basically need to clear the land for solar energy. And land in Europe has a quite high predictive or natural value. So either for agriculture or for natural values. Overall, land allocation. Land is quite well planned in Europe, so there's not so much space that is completely without use. And with more expansions, you will get more competition with existing land uses. And of course, a lot of people will think about rooftop space, like we see so much solar energy on rooftops, which is true. And but you also have to think that if we want to meet a full renewable energy capacity, rooftops will not be able to deliver more than 10% of all electricity. So this is quite limited. So you will anyway need land-based solar, which already expanding quite rapidly nowadays. And then there's always the argument that we can import it on a large scale from Africa, where there's a lot of other space. It's true that there is a lot of space and you will probably not have those issues, but I have put it unrealistic, which I mean on a large scale, because you will have to think of millions of people having to work in a desert with no infrastructure to build this infrastructure. Then you have the issue with connections to Europe, which have losses, but also will have geopolitical consequences that probably Europe wouldn't want all the energy supply to be dependent on a few lines. So in that sense, we put here unrealistic, and we most likely will generate all solar energy in Europe in the end. So this is based on this background. We published a paper earlier this year, me, but also Inigo, who presented earlier, on the land requirements and related land use change emissions of solar energy. And for this paper, we used the global change analysis model, GCAM. GCAM, the benefit of GCAM here is that it connects dynamically energy and land use systems. So basically, what we did here in this model is including solar energy to the interaction. So what this means that, for example, if you switch from gas-fired electricity to solar energy, instead of emissions through the energy supply, you will get emissions probably to some extent to the to land use. And in this paper, we kind of try to quantify this in a few regions, this effect. So first, on the results on land occupation. So this map shows like based on the land regions that the model has, how much land will be dedicated to solar energy if, for example, 50% of electricity in Europe will be generated by solar energy. So you see that in most of Western Europe, this is like 2 to 2.5%. In Eastern Europe, it's 1% because it's less population density as well. But in Southern Europe, like in Spain and Greece, and some parts, it goes up to 3% of land. And then it's hard to maybe imagine if that is less or a lot or not. But you have to imagine that is more than or equal more or less than current urbanized land in Europe. So imagine all cities and roads, all space related to that, and then duplicate it. So it's quite a lot of kilometers that you need. Then where this land comes, or what does it mean, this land occupation? So in this graph on the right, you see on the 0% scenario, how would the land allocation change in Europe from 2015 to 2050 without any land-based solar energy. So like the default scenario, and we will see here. You see here a big shift from natural to managed forests, but also from unmanaged, like barren arable land and pastures to cropland. But then when we mix in certain percentages of land-based solar energy, so this is, for example, 36% of all electricity in Europe will be made by land-based solar energy, so not already distracted rooftop energy, then this yellow share basically comes in, which is solar land, and this mainly replaces agriculture and managed forests in Europe. So it does have a lot of impact on natural uses, on natural land uses within Europe. But of course, since these are predictive uses, those agricultural products and forest products, they would have to be produced elsewhere in the world outside of Europe. So that's what you see on the bottom, like the effects that it has on the rest of the world. So elsewhere, agricultural land and forest land will have to be increased, and this goes at the cost of natural forests, pastures, and grassland elsewhere. So of course, those transitions, they have a impact on emissions, which you try to quantify with this graph. So this graph basically displays the amount of CO2 from land use change per kilowatt hour of solar energy at different levels of penetration in the electricity mix. So so we see here that it goes like well, it's quite a big range. So it basically reach on 5% in the green line at the low penetration levels to 45, or actually more than 50 at the highest point. So there's quite a lot of uncertainty here, and this has to do also with how we do this, which is very important. First of all, these bars, they show the efficiency of panels. So of course, you need much more land if you, for example, install panels of 10% efficiency than panels of 20% efficiency. So the higher efficiency, the less land you need, and the lower the impact. But also the way you manage those solar parks, basically. So if we go towards the most impact will have if you permanently clear land vegetation and put a solar park, and this is what currently happens quite a lot. So you have to imagine something like this, where you completely clear the land and put some solar panels where normally there would have been vegetation. So the other option is, and this is the green line, and it is a little lower end, if you convert this land that you use to like with as much vegetation as possible. So in the case of solar energy, the most beneficial will be like pastures. So you plant you seed grass, and you let you use it for animal grazing, at least of small animals, so that the soil gains the carbon and keeps this carbon. So these are like this could reduce but not completely avoid the land use emissions from solar energy. And if we compare this to the gray area, I put it here on the in the graph as well. These are the emissions from all the other processes for solar energy, so the production of panels and the transport and everything. So if you compare the land use emissions with this, you would say on average you increase the life cycle emissions by about 50% due to this land use effect. So as a conclusion, solar energy in Europe is not without impacts. It likely displaces natural land within and outside Europe, because you need quite a lot of land, and the higher the penetration, the more land use emissions per kilowatt hour. So in absolute and relative terms, you increase the amount of land use emissions. Oh. If you expand more, but also the context is relevant, and this wasn't visible in the graphs maybe, but if you compare this, for example, with natural gas-fired electricity, these emissions are still a lot less. I mean, we talked about 4 to 16% of the emissions from natural gas-fired electricity, so it's still a lot better in terms of emissions than fossil energy. And also much better than, for example, biomass-fired electricity, because Inigo showed in the beginning of his presentation also a graph on the amount of watts per square meter, and this is much higher for solar than for biomass. I will show that like you need 6 to 25. Well, legislative emissions will be 6 to 25 times more with the biomass-fired electricity than with solar electricity. Recommendations from this work will be policies on the siting and land management of solar parks. So not just let the market of clear land where they need, but try to put rules and try to put a strategy on where we want to these solar parks. Also, as much generation as possible in urban areas, which has the lowest impacts on land. And importantly, of course, reduce overall demand. So we don't need so much expansion. They just probably a main take back. Thank you, and this is my presentation.
Thank you, Jan. Thanks a lot. Yes, please.
Okay.
Thanks for this insight. So now we move a little bit on, okay, what can we do? What would be potential policy recommendations? And now I would invite my colleague Diego Marin, who's also working for the European Environmental Bureau, to share his insights.
Hello, everyone. So my name is Diego. I'm happy to be here. Thank you very much for the Locomotion team for giving their results on their project. Still many more to come, I'm sure. So basically, I'm going to go ahead and give a little bit of an overview about what's going on a policy level, what's generally going on here over in Europe, right? So basically, I am going to focus. We're working on a report with Friends of the Earth Europe. The report is going to be centered on green mining, changing the narrative or challenging really what green mining is. And then also making the case of cutting consumption in the EU, right? So then here I have two pictures. I have one picture in Mina do Barroso, which is in northern Portugal, where this lithium mining project is nearing, if things go right, according to the Portuguese Ministry of the Environment. This project would then be operational by next year, 2023, 2024. But this facing a lot of resistance movements on the ground because people generally do not want to have their lands be ripped apart, especially if their land already have an agricultural heritage attached to it. And then also I have on the bottom there, the EU is heavily dependent on lithium, particularly coming from Chile. And then we see this large extraction site in the Atacama Desert, which has a huge impact on the hydrological systems of the region, but also on the indigenous populations as well. And then the general narrative has changed that the EU and industry, general mining industry, has acknowledged that mining in itself is a dangerous and very impactful type of economic activity. However, they can do it green and they can do it sustainably. Which in itself is an oxymoron because it is physically impossible to be sustainable and yet extract resources deep underground. So the idea then, just really quickly, is to, based on the stronger environmental laws in the EU, that it is better to do it in the EU to relieve, it is really a pseudo-moral argument, right? To relieve the pressures on the global south, we therefore need to insource here in the global north, so that we are actually secure our supply chains and relieve pressure to the global south. But this is actually not the argument that's the results that are going to happen on the ground do not tell that, because based on a growth dependent economy, you will not only need to insource further here in Europe, but you will also need to insource in other countries, particularly in the global south, because whatever way we put it, Europe is not self-sufficient in many materials. Okay, so next slide, please. Okay, so then I'm going to talk about Yeah, the targets that we're looking at. So our report that we're working on with Friends of the Earth, we're really arguing that we need to reduce demand. We need to focus really on the demand side, on the economic transition, right? To really not only relieve pressures on the global south, but also to create a new type of society that is more sustainable, more focused on social reproduction, and overall more in tune with the environmental and our planetary boundaries. So as you can see here from this graph, I've demonstrated the GDP and the relation to material consumption in the world. This is a global graph, by the way, but it shows right now from 2009, the actual consumption right now, as is 2019, is around 94 billion tons of materials. And as we can see, the portion of metal ores is continuously increasing. This is also an issue of justice because, as we can see, 1.2 billion of the poorest people account for only 1% of the world's consumption, while 1 billion of the richest account for 72%. Okay, so I'll go ahead and next one. And then here we also have the global material footprints, as is just another a graph really showing the level of disparity between the global north, the highest income countries, and the lowest income countries. Highest income countries consume 13 times more than the lowest income countries, of course. So the idea would be to reduce the type of environmental pressures that the countries in the global north have, to allow the countries in the global south reach a level in which they're able to be more and impair, really. Because we do understand that the countries in the global south do need a type of economic development per se to bring them to better human standards, right? Okay, so the current material footprint of the EU is actually calculated at 14.5 tons, which is higher than the global average, which is around 12 tons, and then much higher, of course, than a just and sustainable level. Yep, so I will go ahead and do the next one. Could you do the next one, please, Kati? Yep, thank you. And this is just another graph as well, explaining the level of increase that we would have in different types of materials. By 2060, we would have, according to the OECD, around 160 billion tons of raw materials. So this is, of course, including fossil fuels, non-mineral resources, as well as mineral resources. Especially sand is the largest raw material as far as raw materials are extracted. However, our report does not focus on this because sand in itself while it has a huge environmental footprint and is extracted in billions of tons all over the world, it is not right now being used as a green extractivism type of end. So this is why we don't specifically touch on sand within our report. Okay, could you go on the next one, please? Kati, next. Yeah, thank you. So we still haven't undergone design, so excuse me for the more ad hoc graph here. But we are arguing for the EU to set binding targets and national material footprint reduction targets for 2030, 2040, and 2050. This particularly looks into, of course, including mining and metal supplies, and then to mainstream all of these targets into all EU-related policies as well as national policies. And this can deal with circular economy, the industry, energy, mobility, renewable energy, and digitalization, for example. So actually, best available evidence shows that we can reduce our material footprint to 4 tons per capita, based on research done by the German Environmental Agency, and as well as Stefan Bringezu, that showed that living within a just limit would be around really 5 to 10, but the most comprehensive would be around 4.4, give or take. And this is, of course, reducing our energy consumption, our material consumption. But this does not mean, by the way, returning to the caves, as some people fear. It is actually just rethinking our society based on social and environmental justice, really, to to return us to a more sustainable and planetary and within planetary boundaries as well. So then, next slide, please. Okay, excuse me really quick. Okay, so this is actually going off of and building really of already European agency particularly mentioned this in a briefing this year, in which we need to really rethink the way we structure our societies, and to really get back into, or to really get into planetary boundaries. And this could result in a combination of, for example, target energy efficiency, recycling, of course, which is very important, material substitution, and then the use of innovative materials, but also leading sustainable lifestyles, right? Now, this is also a case of not blaming the individual, because this is often turned into that argument where the individual is suddenly brought into the responsibility to reduce their consumption, and this is not the case. You know, humans, we generally make decisions based on constraints. So if it is easier to consume more based on the constraints that we have at hand, then we will consume more. So it really requires a governmental systemic change to really get us back into planetary boundaries. Okay, so next, please. Okay, so this is also dealing with transport right now. Oh, excuse me. Okay, so yeah, so the sustainable and smart mobility strategy focuses on really enhancing our electric vehicle penetration in the market, right? And penetration is an interesting word because it's very market oriented, of course. But anyway, so this European sustainable and smart mobility does really allows for some interesting things like double the increase of rail, high-speed rail, which is good. But it also does, by 2035, assume that zero-emission large aircraft will be available. And obviously, this large aircraft will be having a serious environmental impact based on the batteries that would be within these airplanes. And this is, of course, assuming that certain conditions are put into place for aircraft to be zero emissions. But anyway, this is really gears us away from what is actually needed. So transport would then require of how do we conduct society. So what we propose is really to get into a reduction of electric vehicles, right? To enhance and promote cycling, walking, 15-minute cities, 20-minute cities, for example, that other cities in the world are doing. Particularly in Europe, what is interesting, the city of Ghent, for example, has demonstrated a way forward on the increases of bicycle, and really creating a sort of infrastructure which protects the cyclists, right? Most cyclists, for example, are generally into 4 categories. Most people are not the bold type per se. So when they cycle within their cities, they are afraid of cycling because cities are generally made for vehicles. And whether we change our vehicles from fossil fuel internal combustion engines to electric vehicles, we're not really addressing the issue of creating cities that are able to be closer, where people are able to walk more and cycle more. So this is really important, the way we do this. And the way we do this has also to be within an environmental and social justice lens, because it is not enough to just increase transport. This has to be done in an equitable way in which we pay particular attention to those communities that are within the outside, right? Especially, most notably here in Europe, the Roma communities, and then people of color that are usually made invisible within the larger city imaginary. Oh yeah, and it also, sorry, okay, yes. One last thing I wanted to mention about transport, because I don't want to lose too much time, is that the policies that are currently taking place are assuming that we will continue to grow the economy, though we will reduce our environmental impact, which is, resource decoupling, right? Which in itself it's likely not to be possible, or just not to be fast enough to truly create a really good balance within the environment. And promoting cities that are more accessible to walking, to cycling, would therefore decrease the amount of impact that we have, and would also be cheaper. Just generally speaking, cities that are able to quickly decarbonize will be those that are take cycling, walking, and all of those measures into effect. And the next, please, next slide. Yep. And then actually, this is an interesting study that was recently done this year, which argues that cycling is actually 10 times more important than electric cars for reaching net zero cities. And then it also gives some good information about why this is. So for example, and it doesn't really require that much, so everybody riding a bike, though that would be ideal, but it does require a sort of behavioral change, right? So if just 1 in 5 urban residents, for example, were able to cycle for just 1 trip per day, I mean, we're looking at an overall 8% reduction. And this is just small changes in behavior. But of course, behavior has to be guided within a systemic way. So people are not going to ride their bikes unless they feel safe. So there has to be a sort of an understanding of what safe means within the specifics of each individual city, because they're built different, of course. And everyone and every city has different needs as to how they want to operate. But this is the lenses that we should be looking into. And then the next section. Yep. And then also I will speak about low carbon technologies. As we know, reducing energy demand is imperative to reaching net zero. And for example, the 2018 Renewable Energy Directive does set binding targets for renewable energy for 2030 to 38 to 40% to be done by renewables, but unfortunately it does not make a concrete reference to the increase in mineral demand, and just has some more generic references to circular economy policies. So this, of course, requires a fundamental change as well. How do we reduce energy demand? So because energy, business as usual, unfortunately, will not cut it. So this can be done, in our homes and buildings, can be more energy efficient, of course, so that we will not use energy unnecessarily, but also moving less, of course, again, to the transporting system. And then really also localizing energy, right? So who is the energy for? To what ends this is going to? Because it doesn't just suffice to quickly switch energy from fossil fuels to renewables. It does require sort of a democratizing of energy in itself. So energy should go to satisfy people's needs. It is a human right, as it should be recognized as a human right. Without energy, we're incapable, unfortunately, in our industrial societies of doing anything. And the poorest communities are those that also have the lowest energy consumption. But this has to be done in a better way. So it really, right now, energy systems are generally dominated by big monopolies, and big monopolies, if, for example, in the mining industry, the concept of green extractivism would then turn the mining industry into more renewable energies. The issue, though, of course, is that without having an environmental justice lens, we recreate issues in which renewable energy can then satisfy the needs of industry rather than the needs of community. I have a specific case in mind in which geocommunes in Mexico, for example, and the reason why I use Mexico is because the mining industry in Mexico is quite advanced as opposed to here in Europe. They, for example, calculated that a mine in Chihuahua consumed 30 times more the amount of the local municipalities in the area. So it's really an issue of energy democracy at the end of the day, right? To whom are we satisfying the needs? And this would require cooperatives, of course, recognize the energy as a human right, and then also moving toward micro and meso community scale energy systems, so that people can decide how to produce, how to use, how to distribute their energy according to their needs and socio-ecological feasibilities, of course. So that's what I have. I hope I didn't go much over time. Also, didn't want to take too much time because I know that a lot of people may have questions. So in the report that we have with Friends of the Earth, is of course going to be, we're still figuring out the policies, of course. So if you have any ideas, I will provide the next slide, please, Kati. Yeah, so I am providing my email here. If you have any ideas, if you want to exchange as well, we would certainly like to discuss with you. This report would more or less be done by July, but we're planning to launch it in September when there will be an event going on, and then we'll have a webinar and we'll go more into detail about this. This is just what I have related to the locomotion project as well. So yeah, thank you very much, and hope to have a good discussion.
Thanks, Diego. Thanks a lot for your input. So we only have 4 minutes left, but I saw that Marga and Dirk-Jan and Inigo also responded to a lot of the questions that we had in the chat. So maybe Diego, you can answer the first one, like how can we make lithium mining more sustainable?
Yes, sorry, I was just about to answer to the chat. So yeah, so how to make mining more sustainable? I think the issue within the question is, and it really is a dominated narrative by the mining industry, right? To sort of create the idea that mining in itself is necessary for renewable technologies, for getting us to net zero emissions. And actually, processing against mining sort of becomes foolish, or being against net zero, which is not the case. It's an environmental justice issue. But so how to make mining more sustainable? I think we're asking the wrong question. The best question would be how to decrease our demand. In the case of lithium, for example, there are some technologies that are more energy intensive than others. For example, geothermal lithium is, though it's not applicable right now on a huge scale, but it does offer a less type of environmental footprint. However, this has to be taken into account. It doesn't matter how sustainable the mining industry can be. What matters most is what is the impact on the local communities, because mining, for example, cannot just happen anywhere. It has to happen in specific cases due to the geology of the region, due to the economic feasibility of the project itself. But the people that are living there, those are the people that matter the most, right? So yes, we can make mining more sustainable per se. We can, or not sustainable, I shouldn't use that word, but we can reduce the impact of mining. But then again, that takes us away from the question of justice, right? So the most important thing should be the local communities, the local input, and whether they even want to have these projects on the ground.
Okay, thank you, Diego. Thanks a lot. So, I mean, considering that we only have 2 more minutes, I mean, I just want to ask Inigo or Dirk-Jan or Marga if you, in 1 minute, just want to react or to some of the questions you already answered in the chat. Please feel free to do so.
Well, I don't know, Inigo, if you want to answer to the one that said that was a new invention by a Philippine they send a link of an invention of a Philippine.
I kind of responded. Sorry, I already responded to that. It was a follow-up comment for another question.
Okay, that was just a follow-up from another question. Yeah, I was just thinking, because you have typed your answers already, but I was thinking maybe you would take 1 minute to elaborate on something, but if not, it's also so fine. Otherwise, I think considering the time, I would close now. I want to thanks again to all the participants and also to our speakers for the really interesting insights. And I think what we can say, what we can agree on, that we really need a more holistic approach when it comes to renewable energy and transition, where it makes sense to have a more deeper and holistic approach and look to the hidden to the benefits, and but also the limits and the threats in a way. And I also feel it's very important to apply a social justice lens also when it comes to renewable energy transition. So I just wanted to invite you just again to please follow our Locomotion channels to be or keep yourself updated for the next results and events that we will share on these channels. Yeah, thank you very much and have a really nice afternoon. Bye-bye.
Bye-bye. Thank you.
Thank
Bye-bye.
you.
Thank you.
Bye.
Bye. Thank you, everyone.